Linda Maoy. I am from the South African Population Research Infrastructure Network, which stands for SAPRIN. We are a network of health and demographic surveillance systems. Here in South Africa, we've got about 6 HDSS nodes that we manage here in Southern Africa. And I am the senior data scientist responsible for ensuring data quality across our 6 HDSS nodes. So today, I'll be presenting on a follow-up course that already started last week, which is titled Application of AI and Machine Learning in Mental Health Data. My colleague, Dr. Amelia Taylor, already took you through the first part of the course. I do believe it started last week, Friday, where she was basically highlighting the different applications of AI and machine learning in the mental health sphere. So I won't go into that into detail today, because this is just a follow-up from what she's already shared. In the first course, you are also focusing mostly on supervised learning, machine learning algorithms. For this course, it is part 2. I'll be focusing on another type of machine learning algorithm called unsupervised learning. Okay. So there's my picture right there. Like I said, I'm from SAPRIN. That is our logo right there. We are hosted at the South African Medical Research Council, and we are fully funded by the Department of Science and Innovation, which is a department in the Republic of South Africa. So today we're going to be looking at 6 high-level topics. We're just going to do a brief introduction to R. I'm sure some of you are joining us for the first time today, so I just want to make sure that we are all aligned in terms of the tool that we'll be using today. This is not going to be a comprehensive introduction to R. It's just very, very high level. I do believe that there were other courses before this one that dealt specifically with the R programming language. In section 2, we'll be looking at unsupervised learning. So just a brief introduction to unsupervised learning. We'll look at the application of unsupervised learning using a machine learning algorithm called cluster analysis. In chapter 4, before we actually apply that machine learning algorithm, we need to first understand how to prepare our data for cluster analysis. Very, very important. In number 5, then we'll be creating clusters through our cluster analysis algorithm. And number 6, we'll be looking at plotting and interpreting cluster results. Okay, so that's basically the synopsis of what we'll be covering today and possibly tomorrow. So I'm hoping that we can wrap up everything by today. However, there is an opportunity for us to finish off the course tomorrow if we don't get to finish today. Right. Any questions before I continue? All right. So Nafata is asking about the materials for today's session. Have they been already shared? I don't think you'll need anything external from what you already have. Just a show of hands. I just want to check something quickly. Do you guys have the synthetic depression data set? So this data set has been used for other courses as well. That's synthetic_depression_data.csv. Please type yes in the chat or no in the chat if you don't have access to that data set. Okay. So what I'm going to do is, okay, I'm going to put it right here in the chat so you can download it from there. So the nicest thing about Zoom is that you can actually download stuff from the chat. So if you go to the chat there, you'll see where I typed there. Just look for where I have uploaded a data set. It's called synthetic_depression_data. Okay, download that data set. That's the data set that you'll require. Okay, I'm also going to be nice. I will also give you the course notes for this course. So I'm just going to upload them as well there. So you'll see the course notes written Introduction to Unsupervised Learning 2024. Okay, so you can download those course notes and download the CSV file. Anyone having issues downloading that file from the chat, from the Zoom chat? Let me check. Samuel, were you able to download that file? Because you initially said no. Sam? Okay.
I downloaded it. I'm trying to open it.
Perfect, perfect. Atem? Did you download the file? Synthetic_depression_data.
So I have it now. It has opened.
Okay, cool. Right, looks like we are all sorted. Let's get back to the course. Just gonna reshare my screen again. Alrighty, so thank you. All right, so now let's start with the quick introduction to R. Okay. So for this course, we're going to be using a programming language called R, which most of you should be familiar with because it is the programming language that has been used for previous courses before this one as part of the series of courses under this program. Okay. Now, for those who are not familiar with R, R is a high-level programming language that is primarily used for statistical computing as well as data visualization. Its core function is on statistical analysis and data visualization, unlike other programming language like Python or Java, which are general purpose programming languages. So this is a specific language that has been designed for specific use cases, and it's geared more towards statistics as well as data visualization. R is open source and licensed by the GNU project. Basically means that it is free to download and free to use. Okay, so if you just go to Google and say Google for R as a programming language, download, you can download it freely on your computer and use it freely. Okay, just a bit of history. It was created in the early 1990s by Ross Ihaka as well as Robert Gentleman, who I believe were both statisticians. Okay. Now we've got RStudio, which is an interface to R, okay, or what we call an IDE or an integrated development environment for R. It basically makes it easy to develop R programs, okay? It is nothing but just an interface. So there are two things that you require to run an R script. You first need the core installation of R, as well as an IDE or an integrated development environment. And they come in various flavors, okay? One of them is RStudio. I'm sure you guys are familiar with other flavors. Maybe in the next question, just to check, which IDE do you use for programming in R? For those who are already familiar with R, which IDE do you use for programming in R? You can type it up quickly in the chat. Do you guys use RStudio? Are you fans of Jupyter Notebooks? Who's brave enough to say Emacs or Eclipse? RStudio, RStudio, RStudio. Okay. Anyone else? Okay, RStudio. All right, cool. Looks like the majority of us use RStudio for R programming. Okay, so that is the IDE of choice. Okay, so in this particular course, we'll be using RStudio for developing our R scripts. Okay, any questions before I continue? Any questions, any burning issues? No. All right. So I'm going to do the first demonstration. And for the first demonstration, I'm going to ask you guys that you open up RStudio. Like you guys to open up RStudio. And the first thing that we're going to do with RStudio is that we're going to first make sure that we've installed RTools, okay? I did request that you guys install RTools as a prerequisite for this course. So to check whether RTools has been installed, I'm just going to run this little script. Maybe let me make it bigger. I don't know if I can make this bigger. I think that's it. I'm not sure how to make it bigger. I'll check. So you run this piece of code, sys.which make. And if I run this piece of code, if I see this message coming back from the R console, that basically says to me that RTools has been installed. So my installation here is for RTools 43. Then the second thing I want you guys to do is I would like you guys to install these packages. Okay, so I'm just gonna run this piece of code. Don't worry, you don't have to do it right now. There's an activity coming up that will require you to install these packages. Okay, so I'm installing all these packages here that I'm going to be using for this course. Okay, I'm just gonna say no. I think one of the packages is already installed. If the package is already there, then there's no need for you to reinstall it. For those who are doing this for the first time, I would encourage you that you install all the packages. Okay. Okay, so that was the first demonstration. Now I would like you guys to do the activity, which is exactly the same as I've done for this demonstration. Okay. So this is the first activity. I'm giving you 5 minutes. All you have to do is install the required packages. Okay. So one thing I want you guys to be aware of, there's no need for you to type all these things out. They're just notes so that you can understand what each package is for. Okay. So there's no need for you to type all of these out. All right. All you have to do is just install these lines. So just write out these lines, install.packages, dplyr, and all of these ones. Okay, simple as that. Okay, 5 minutes. Yes, Samuel?
Okay, yeah. Considering the short time we have, I'm thinking, is it possible to, I don't know, maybe you might be asking for too much. Is it possible to just paste this at the chat so that we can now take it and then know what to do with it? To make it easier.
Yes, I mean, you do have the notes. I've given you the notes. So you can copy and paste from the notes that I've shared with you for the course.
Okay, all right, thanks.
Yeah. I've put the timer right there so that we're all aligned in terms of 5 minutes. Okay, I'm sharing the notes again. Please look out for them in the chat? They're coming now. There we go. So Abigail as well as Willie, you should now have access to the notes. Sam, you had a question?
No, I'm okay.
Okay. Okay, so let me know in the chat once you've done with installing the packages. If you install the packages, then we can move ahead. Thank you, Martin. Okay, guys, we've got less than 20 seconds. We need to move. I only see one person who's able to install all the packages. What about the rest? Okay, 2 more minutes and then I wrap this up. We move on. Let's move, Priska. Must install those packages, Priska. Thank you, Nondumiso. Thank you, Sharon. Thank you, Senior Clinton. Thank you, Caroline. Okay, we've got less than a minute and then we wrap this up and then we move on. Okay, so we move on. So thank you, everyone. So that was part of the first activity that we needed to do for this course. The first part was to verify that we've installed our tools. If you don't have our tools, I don't think any of these packages will be able to. So it's very important that we need to have our tools to be installed first. And then you created an R program and you named it clusteranalysis.R. And in the program, you basically wrote these lines of scripts to basically install the packages that we are going to be requiring for this particular course. Okay, I won't go through all of the packages. I think all the explanations about each package is right here in front of you, so you can read that on your own. All right, any questions before I continue? All righty, no questions. So now we'll be talking about unsupervised learning. Okay. Unsupervised learning is a type of machine learning that learns from unlabeled data. By unlabeled data, we basically mean that the data does not have any specific predictors assigned to it, as well as specific target assigned to it. Now, when you're doing supervised learning, what happens is that you specify a target variable and you also specify predictor variables. Now, in unsupervised learning, you don't do that, okay? So that's why we say that the machine learns from unlabeled data. You don't specify any predictors or any target variables. This means that the data does not have any pre-existing labels or categories like your supervised learning algorithms. Another example of a supervised learning algorithm that most of you are familiar with is your linear regression model, okay? In the linear regression model, you've got a number of predictors or input variables, and then you've got the predicted value, which is your target. Now, the goal of unsupervised learning is to discover patterns and relationships in the data without any explicit guidance. Okay, so this picture basically summarizes it nicely, where you've got an unknown data set here. It goes through your unsupervised learning algorithm. It gets processed, and then your model starts to see some pattern there, and then it basically spits out this data. Okay, so this is a simple way of clustering data. Okay, so you got data which is mixed up like this. It goes through all these phases, and then it gives you an output like that. Okay, so with unsupervised learning, you basically don't know what you're looking for, or what we call data mining. You're just basically mining the data, but you don't know exactly what you're looking for. You're basically using unsupervised learning to find patterns within your data that otherwise are not as obvious to you. Okay. Now, here's a quick summary of the differences between supervised learning and unsupervised learning. So in terms of the input data, your data has got labels for supervised learning. That basically means that you specified what your predictor variable is and what your input variables are. Now, in unsupervised learning, no predictor variables, no what you call this, target variables. When you use supervised learning, when you know the expected outcome and what is being looked for. So for instance, if I want to predict what the weather is for tomorrow, if you don't know the expected outcome and what is being looked for, then that's when you use unsupervised learning. Here is data that here's my data set, which has got a number of variables, mental health, climate data, and all of these things. I'm not really sure what I'm looking for, okay? Can the machine learning algorithm tell me something which is interesting about that data? Now that's where you go through unsupervised learning, okay? The different problem types, the one that you're most familiar with for supervised learning, that will be your regression and classification problems. For unsupervised learning, clustering is one, dimensionality reduction is another, or some of you might call it principal component analysis, or PCA, as well as association. The goal for supervised learning is to predict outcomes for new data based on training data. And the goal for unsupervised learning is getting hidden patterns and useful insights from large data sets. Okay, so the output here is your target values or your predicted labels. The output for unsupervised learning will be your clusters or association rules. In terms of mental health, these could be some of the what you call this use cases that you can apply for supervised learning versus unsupervised learning. Okay, any questions before I continue? Okay, so this is basically a quick summary on the differences between what you've learned from Friday up until this week on Tuesday versus what we are doing in this particular course. So Dr. Amelia went through supervised learning. I am focusing on unsupervised learning. Okay. Now here we look at the types of unsupervised learning. Okay. The first type you've got is cluster analysis, which we'll be focusing on in this course, which basically involves grouping untagged data or unlabeled data based on their similarities and differences. Then you've got association rule mining. This type of unsupervised machine learning takes a rule-based approach to discovering relationships between features in a given data set. This, in retail, they call it market basket analysis, whereby they want to see the correlation between various items and how they relate to each other. So for instance, when you go out to the market to buy bananas, as well as toothpaste and other items, they want to see which items go mostly together or are bought mostly together. Okay, so that is basically an example of association rule mining, or what we call market basket analysis in retail terms. Then you've got dimensionality reduction, which is principal component analysis, which basically seeks to transform data from high dimensional spaces to low dimensional spaces without compromising meaningful properties in the original data. So here you are basically trying to find features of interest, okay? For those who have used PCA, it's able to find patterns which are most prominent in the data in ascending order. So, no, sorry, in descending order. So the first pattern will be the one which is most prominent in the data, followed by the second pattern, which is the second highest prominent feature in the data, and so forth. Okay. But for the purpose of this course, we'll be focusing on cluster analysis. So these are some of the applications for mental health, like in unsupervised learning algorithms like K-means. We can use that to identify types, subtypes of disorders, different symptom profiles, or even segments of population that respond differently to certain treatments. In the dimensionality reduction, we can use that to reduce the dimensionality of mental health data while retaining important information. So for instance, if you've got a plethora of the mental health data and you want to extract key features, you can use techniques like PCA to basically retrieve those key features in the data while retaining important information. Association rule mining, you can also use that in your mental health data to basically find associations which might not be immediately obvious. This could include relationships between certain symptoms, comorbidities, or factors that influence treatment outcomes. It's all good and well to talk about the benefits of using unsupervised learning algorithms, but of course, sometimes they come with their own challenges. And these are some of the challenges that I've listed with regards to using unsupervised techniques. The first one is around data quality and variability. Not just mental health data, but different types of data sets can be noisy, incomplete, as well as subjective. Unsupervised learning algorithms may struggle to effectively handle these challenges, which may lead to biased or unreliable results, especially missing data. So you need to ensure good quality of the data, address variability in your data in order for you to obtain meaningful insights. The other issue is around the lack of ground truth, which basically talks around the evaluation as well as performance of unsupervised learning algorithms objectively, okay? So with supervised learning algorithms, you've got a way to benchmark these algorithms, but something for unsupervised learnings algorithms is quite difficult. Something similar for unsupervised learning is quite difficult. So without clear benchmarks, assessing the accuracy as well as relevance of these results coming from your unsupervised learning algorithms could be challenging. Another one of my favorite is the curse of dimensionality. And this not only impacts unsupervised learning algorithms, it also impacts supervised learning algorithms. So the curse of dimensionality, in plain simple English, basically means that the more columns you have or the more input variables you have, the more data you require, okay? So if you only working with, let's say, 10 rows of data and then you've got 100 columns, your results are going to be unreliable, okay? So there's no stability in the machine learning algorithms to give you any useful outcomes. So for the curse of dimensionality, there are other ways in which you can reduce that dimensionality, which might be choosing variables that make sense or choosing variables which are relevant to your study, as well as reducing variables that are highly correlated to each other. So for instance, having a variable like your salary as well as the tax that you pay on your salary doesn't really make sense, because both of those variables will be highly correlated, because the more the salary you earn, the more tax that you pay. So there's a very high correlation between those two variables. So one of them has to be removed. So one of the, the term that we use for that is what we call redundancy, okay? You don't want redundant data. So firstly, to curb the curse of dimensionality, you need to reduce redundancy and then remove irrelevant data. The other thing is around clinical validity and utility. So while unsupervised learning algorithms may uncover interesting patterns or associations within mental health data, their clinical validity and utility remains uncertain. So we cannot just take what the algorithms are saying at face value. We need to go through rigorous validation and collaboration with domain experts, okay, to make sure that the results are making sense. Any questions before I continue? Okay, you guys are very quiet. I'm getting worried. Are you guys still here? So let me check quick. Martin Nabwana, are you here?
You're doing very well.
Okay. All right. William Kono.
Yes, I'm here.
Okay. Now I'm just checking if you guys are still here. All right. So now we're moving to cluster analysis. All right. So we've just done nice introduction to unsupervised learning. Now we're going to cluster analysis. So there are a multitude of definitions for the field of data mining and knowledge discovery. Most center on the concept of pattern discovery. For example, Professor David Hand, who's a professor of statistics at the Imperial College, defines the field as the discovery of interesting, unexpected, or valuable structures in large data sets. This is possibly made by the ever-increasing data stores brought about the era's information technology. Although David Hand's pronouncement is grandly promising, experience shows it to be overly optimistic. In his defense, Professor David Hand is well aware of the limitations of pattern discovery and provides a guidance on how this analysis can fail. These failings often fall into 6 categories, which is poor data quality, opportunity, interventions, separability, obviousness, and non-stationarity. So I just want to spend a bit of time just to define all of these. So the poor data quality refers to data that is noisy, incomplete, inaccurate, or inconsistent. It can limit pattern discovery by introducing biases into the analysis. For example, in mental health data, poor data quality might manifest as missing or misrecorded symptom information, leading to unreliable patterns or misleading insights. The other one is opportunity. This limitation refers to the fact that some patterns may not be present in the data or may be underrepresented due to limitations in the data collection or sampling methods. So some aspects of mental health phenomena may be difficult to capture or measure accurately, or some might even be very, very, very rare, resulting in missed opportunities for pattern discovery. Another example is, or another issue is intervention, that is, taking action on the process that generates a set of data can destroy or distort detected patterns. For example, let's look at the example of fraud. So fraud detection techniques lead to preventative measures, but the fraudulent behavior often evolves in response to this intervention. So interventions can also skew up the data in the long run. Separability is a very simple one. It basically refers to the degree to which different patterns or clusters in the data can be distinctly separated from each other. In some cases, patterns may overlap or be inherently intertwined, making it challenging for unsupervised learning algorithms to accurately identify and delineate them. This can lead to ambiguous clusters that obscure the meaningful patterns within the data. Now, this one is my favorite one, obviousness. The obviousness limitation occurs when patterns discovered through data analysis are already well known or intuitive, providing little new insight or value. In mental health data analysis, this might occur if algorithms identify patterns that align with common knowledge or existing understanding, or existing clinical understanding without uncovering novel insights. However, this could be useful for validation purposes. So the goal of pattern discovery is often to reveal previously unrecognized relationships or trends. The last one is non-stationarity, which basically refers to the changes in the underlying pattern or relationships within the data over time. Mental health phenomena can exhibit dynamic and evolving patterns, which might challenge the assumptions of stability and consistency underlying many pattern discovering algorithms. Changes in patient populations, treatment practices, or environmental factors can introduce temporal variability into the data, requiring adaptive analysis methods to account for the non-stationarity effectively. Okay, so you need to be cautious about all of these things while you are doing cluster analysis. Okay. So unsupervised classification, also known as cluster analysis, basically attempts to group training data set cases based on similarities in the input variables. It is a form of a data reduction method because an entire training data set can be represented by a small number of clusters. Their groupings are known as clusters or segments, and they can be applied to other data sets to identify new cases. It is distinguished from supervised classification, which was discussed in the previous course. The purpose of clustering, ladies and gentlemen, is for exploratory, is for data exploration, sorry. For example, you want to segment existing study participants or patients into groups, and associating a distinct profile within each group might help future strategies. However, there is no guarantee that the resulting clusters are meaningful or useful. Okay, so you need to take that with caution. So I'm now going to introduce the k-means clustering algorithm. So for the purpose of this course, we'll be using the k-means clustering algorithm, which is a centroid-based clustering algorithm, where we basically calculate the distance between each data point and a centroid to assign it to a cluster. The goal of this algorithm is to identify the k number of groups or the k number of clusters in the data set. Okay, so I'm going to go through this code very quickly, and then I'm going to show you the same code in picture 4. So here we've got a function here that basically computes our clusters. So this is our cluster algorithm. So you first start by initializing k centroids. Okay, so you first start by guessing how many clusters you want to have. Okay, so there is a scientific way to do this. I will show you when we do the demos. But first, you need to initialize k centroids. So you basically pick out any number of clusters that you want to see. So it could be 3, could be 2, depending on what you want to be looking at. But like I said, there is a scientific way of doing this. Okay, so here we just initialize with, let's say, 3 k centroids. So it's going to basically place 3 centers in that particular data set. And then for each point, you are going to basically initialize it with -1, since it does not yet belong to a particular cluster. So remember, we're going to only define 3 clusters: cluster 1, 2, and 3. That's what we've chosen, right? As our number k. Okay. So we first going to, sorry, here where it says initialize cluster labels, we are going to initialize them with -1 for each point as points. So to basically say that they don't belong to any cluster as of yet. Okay. Then we set the convergence criteria to false. Okay, so this is going to be very important later on. So here you go to a loop, a while loop. So in that while loop, you say while not converged. So while the algorithm has not yet converged, this is what you need to do. You need to calculate the distance. And when we talk about the distance, we talk about the Euclidean distance, okay? From each point to each centroid. So remember, you chose 3 random centers, okay? In the beginning, okay? So now you're gonna take each point in the data set, and you want to calculate the distance from that point to the centroid. Okay. After that, you update the point in the label array with the closest centroid. So for instance, if point 1 was the closest to centroid 2, it means now the label array for point 1 is going to be updated with the first, with the number 2. Okay. If point 2 is closest to, let's say, centroid number 3, it means now that the label is going to be updated with 3. After doing that, you're going to calculate new centroids by taking the mean of the points in each cluster. So now you've got 3 clusters, okay? 1, 2, 3. Now you're going to calculate the new centroids by taking the mean of the points in each cluster. And then you repeat this calculation until the mean of the old centroids is equal to the mean of the new centroids. Okay, so this calculation is going to repeat and repeat and repeat up until the time that the old centroids, the mean of the old centroids is equal to the mean of the new centroids. And if that is true, then it will set the convergence criteria to true, and then this loop is going to end. And then you return the number of clusters. Okay. So what is the best minimum K to consider? So the best is 2. You need to have at least 2. I mean, that is like the minimum. But like I said, I will show you how you can actually determine the number of clusters that you need in your data. Okay. So in picture form, so basically I'm going through the last algorithm, but now I'm explaining it through this picture, and I hope it makes more sense. Okay, so before we start, we'll need an interval measurement. By interval measurement basically means that we need numbers. Okay, so you can't use text data for this. Okay, so all your columns must have numeric values. Okay, so that's why an interval measurement is recommended for k-means clustering to produce non-trivial clusters. Okay. So in this example, we selected 1, 2, 3, 4, 5. So we said, okay, we're going to select 5 random distinct clusters, okay, spread across the data. So this is our starting point. Okay, so these are randomly assigned. Okay, but they have to be distinct. Okay, so we've got these 5 points here. So what we're going to now do is we're going to be calculating the distance of each point. So you can clearly see that. So let me take this point, for example. So I'm going to first calculate the distance between this point and this centroid here. Calculate the Euclidean distance between this point and that centroid there, this point and that centroid here, this point and that centroid there, this point and that centroid there. Okay, that's the Euclidean distance. After that, I check which is the shortest distance. Can somebody tell me which one is the shortest distance? Is it 1? Is it 2? Is it 3? Is it 4? Or is it 5? Which one is the shortest one? It is 1,
3.
right?
5.
Okay, let me start
1.
again.
5.
Okay, so let me start again. So let
One.
me do this so that we are all clear. So this is 1, this is 2, this is 3, this is 4, and this is 5. Okay, so I'm starting with this point here. I'm starting with this point here. You see this point here. Just want to explain how the algorithm works. So I'm going to calculate the distance between here and centroid 1, distance between this one and centroid 2, distance between the point and centroid 3, distance between the point and centroid 4, sorry, and the distance between that point and centroid 5. Okay? Which one is the shortest distance? Hello?
1.
It is 1, right? Good, good, good. So that's the shortest distance. And therefore now, what's going to happen now is that this point now will belong to this centroid for now. And then we do that for all the points. So for instance, if I had this point here, it will first start. Okay, what's the distance between this point and centroid 1, this point and centroid 2, this point and centroid 3, this point and centroid 4, this point and centroid 5. And of course, it is this centroid which is the closest. Are we all in agreement?
Yes.
Okay, cool.
Yes.
Okay, cool. So that's basically how it works in the background. All right. So now you can clearly see now all of these points here have got the same color or the same label as their nearest centroids. Okay. So the Euclidean distance from each case in the training data to each cluster center is calculated. Cases are assigned to the closest cluster center. And this is the formula for the Euclidean distance. So I want you guys to know that because the distance matrix is Euclidean, it is important for the inputs to have compatible measurement scales. Unexpected results can occur if one input's measurement scale differs greatly from the others. And that's why it's very important for us to normalize our data before we even do this clustering algorithm. But we're going to go through that when we do that demo. Okay. Are we all together still? Okay, I haven't lost
Yes, we
it.
are.
Yes.
Okay, cool. So after we calculate the the distance from each point to the cluster center, what we're now going to do, we are going to calculate the mean of all the clusters. Okay, the mean of all the clusters, the mean of all the clusters individually. What this mean is going to give us is a new center. Okay, it's going to give us a new center. All right, very, very important. What the mean of each cluster now is going to do is going to give us a new center. And after giving us a new center, we're now going to reassign the cases. So now we've got a new center. We are now going to go back to our algorithm to check. Is this point closest to this one? Or is it closest to this one? Closest to that one? Closest to that one? Closest to that one? Okay? After calculating the new centers. Okay? So it will continue over and over and over and over again until we find that the mean of the new centers. So let's say in the previous part, we ran this and the mean there was 5. Okay, let's say the mean was 5 all around. If I now calculate the new mean, if the new mean remains as 5 for all of these clusters, then convergence has taken place. Okay, then I can exit. If let's say, for instance, this was 5, 5, 4, 5, 5, and then when I run the algorithm and this changed, it's no longer 4, but it's 5, it means now new means have to be calculated for all the clusters. So it will repeat over and over and over and over again until there's no differences in the means from one, from one step to the next step. Okay, so it brings me back to this part of the code where I said that if the new centroids are equal to the old centroids, then set the convergence to true. So basically means that if the means are not different, if I'm going to be running this code and the means remain the same for the next step, if the means remain the same for the next step, then convergence has taken place. Okay, and now I've got my cluster centers. All right, any questions on that?
Please, could you go over it again?
Must I go over it again?
Please, please.
Okay. Cool. So first thing, sorry, what's your name?
Bisola.
Bisola. Okay, so this is very simple. We are going to first start by guessing how many clusters we want to have. Okay, so in this case, we have guessed that, you know, maybe we need 5 clusters. Okay, and then you've got different algorithms that can basically place these clusters around your data, but they have to be distinct values. Okay, so it places these cluster centers around your data. Okay, so that's the first part. So the first part is you guess the number of K clusters. Okay, there is a scientific way of doing it, but I'm just giving you like the simplest way. The first simplest way, you guess the number. Okay, here we've got 5 centers. Are we all together? Okay.
Yes.
Then, so think about these as points in your data, right? So you're going to first look at the first point here. So let's start with this point here. We're going to calculate the distance between this point and the first cluster center. We take the same point, we calculate the difference between this point and the second cluster center. We calculate the difference between this point and the third cluster center, and we do that for the fourth cluster center as well as for the fifth cluster center. Okay, now you measure the distance by just looking at these distances. Which one is the closest to this point? Which cluster center is the closest to this particular point?
1.
Yeah, 1. Okay, so that basically means that 1 here, this particular point is now going to belong to this cluster. Okay, and you can clearly see that even with this particular point, without even having to calculate the Euclidean distance, it belongs to this particular cluster. Okay, so each point here is going to basically be matched to a particular cluster center based on the distance between the point and the cluster. Are we together?
Yes, thank you. I get it now. Thank you.
Yes.
Oh,
Good.
sorry, great. Does this
Hello?
mean that you can choose arbitrarily any point in this scatter plot? In this scatter, that is?
Yes.
Okay.
Yes. Any point. I mean, we're gonna start, but every point is going to basically be measured in terms of its distance to each of these centroids.
Okay, great.
Yeah.
Sorry, can we say that this is a Cartesian plane?
And what?
The distances, whatever, the blue area, the whole of it's a Cartesian plane, so that we have the X and the Y, and we have a scale on the X axis and a scale on the Y axis, and therefore the distances are measured by that.
Yes. These are Euclidean distances, but remember, here I'm only giving you the, what you call this, the example, if it's only like, let's say, data defined by X and Y, but you can have data defined by more than one point. For instance, this algorithm here, it doesn't show it nicely, but per observation, you can have multiple variables, right? So you should not just limit it to 2 variables. You can have multiple observations, and each of those observations, you're going to calculate the distance from one variable of observation 1 to the other variable of observation number 2, and so forth.
Thank you.
Okay, cool. Any other questions?
Yes, please. I would like to ask, what if you have a variable that has quite almost equidistance from 2 plus? What do you do?
No, that will be handled by the Euclidean distance. Remember, here you're just calculating distances here.
Yes.
Yes.
Okay.
Yeah, so here you're just calculating distances. You are just focusing on distances, nothing much. Okay. So I think, so that was basically the theoretical part of what I wanted to cover for this course, so that we have a good understanding of how clustering works in the background. Okay. So I'd like us to maybe take a 5-minute stretch break, and then we continue. Okay. So I'm just gonna put a timer here. It's just gonna be a 5-minute break, and then we come back. Okay, I'll be back in 5 minutes. Okay. All right, welcome back, everyone. Let me just check. Caroline, are you there? Caroline Mugo.
Yes, I am.
All right. Right. So I think let's carry on. Okay, cool. So we're now going to move on to preparing data for cluster analysis. So remember, I shared with you a data set that you guys have been using for the past couple of weeks. So there's no change to that data set. It's called synthetic_depression data.csv. That is the data set that we'll be using for this course to do a simple cluster analysis. Okay. So this data is called social media and mental health data set. There's the reference for the data set, which basically examines the impact of Facebook's introduction on mental health outcomes among college students in the United States.
Can you share again this data?
Must I share the data again?
Yes. I missed
Okay.
it in the link.
Okay, so there we go. I'm sharing it again on the Zoom chat. So it was shared. This is the same data set you guys have been using for the past couple of weeks. So it's not a new data set. I feel like you guys are more of experts than me on this data set. Okay. So there we go. So we'll be using this data set for all our examples going forward. Okay. So what we first need to do is we need to set up the R environment. Okay. I'm sure you guys have already installed R. So we need to set up the R environment for our use. So what we are going to first do is we're going to run this piece of code to basically load in the libraries that we require. Okay, that will be the library stats, the library deep layer, the ggplot2, Fortify, Factoria Extra, Cluster, as well as Caret. So these are in your notes. You can copy and paste from your notes. But I want you guys to check something very important. I would like you guys to take this synthetic depression data. Okay. So I'm just going to do a copy on it. I want us to go to Windows C on your C drive. Maybe create a folder called workshop. Okay. Workshop. And then create another folder called R programs. And then save your data set there. Okay. But you can save it anywhere as long as you know where the path is. Okay. So let me take that back again. So you copy the data set, the synthetic depression underscore data. You go to your C drive. From C drive, you go to workshop. You create a folder called workshop. You go under R programs or name it whatever you want to name it, and then paste your data set there. Okay. After you've done that, you're going to run this command, the get wwd command. So this get command will basically show you in which directory you're in. So it tells me that I'm in the C workshop R programs directory, which is the same directory as my data set. Okay, which is fine. If I'm not in that same directory, what I can do is I can run this set wd. So it's called set working directory. I specify where the working directory should be. So in this case, it is C workshop R programs. So this is basically me setting the directory where the data is located. And after running this program, so let me just run it now. And I run the get working directory. It should tell me that I'm in the right directory, C workshop R programs. Okay.
Excuse me, where can we get the node?
The nodes are posted in the chat.
I couldn't find, sorry.
Okay, I'm posting them again. Right, just hold on.
I've posted them.
Okay, so Joel has posted them. All right. So, but you don't really need the notes. The notes are just there for copy and paste. So here is the activity for you to follow. So you've got 5 minutes to do this. Okay. Yeah, the notes have got the code, Florence. Yeah, this thing doesn't want to work. Okay, it's fine. I will count the 5 minutes. So you've got 4 minutes to go. Okay, please let me know in the chat once you're done. Thank you, Loji. Right, guys, you've got less than 2 minutes and then we carry on. Thank you, Mercy and Eunice. But you guys didn't give me the answers. What is the output of R in the R console after typing get WD? Thank you, Senior. Okay. All righty. So now we're going to move on to demonstration number 3, which is basically accessing the data. So to access data, it's quite simple. So we now are in the same directory as our data set, okay, by specifying the set working directory. And now we need to read in the data set. So we're going to be reading this data set into what we call a data frame. Okay, so this DF, you could have named it anything, but because I'm working with a data frame, I'm just going to call it DF. Okay, so I just highlight this piece of code and I run it. And immediately on my RStudio environment page, I can see DF there. Okay, and if I expand it, it shows me all the variables which are contained within the data frame. So I've used the read.csv function to read this data set, synthetic depression, into a R data frame. Okay. So I do believe that your next activity is around that. Okay. I'm not going to give you 10 minutes to do this. I think it's too much. So let's make it like 5 minutes. All you have to do is type out this code, data, read.csv, synthetic depression data. And then in the chat, I would like you guys to give me the answers. How many rows and columns are in the data set? What type of column is sex? And the last question is, can we use the variable sex as input into the clustering algorithm? Okay. So it's not 10 minutes. It's going to be like a quick 5 minutes. So guys, when you give me the answers in the chat, don't just say done. I need answers. You need to tell me how many rows and columns are in the data set. What type of column is sex? And the last question there is, can we use the variable sex as input into the clustering algorithm? Yes or no? Okay. Okay, Florence, you said something very important. Can you please explain what do you mean by encoding? So you say we can use the sex variable after encoding it. That's from my Python view. What do you mean by that?
Okay, I was trying to mean that like when we encode sex, like we give it maybe 1 for male, 2 for female, something like that. Because we cannot use character or strings in models, machine learning models.
Okay, all right. That's
Yes.
good. That's good. Okay. Yeah, I like that. Anyone else? So basically, Florence, what she's saying is that because the variable is a character, if you look at the sex column, it's got a value for male and female, which are characters. You can't use that in a machine learning algorithm because how does it calculate the distance between characters? Okay, so it needs to be a number. So she says that we need to encode that variable sex so that it is represented by numbers instead of characters. Okay, which is correct. Okay, however, we need to take that discussion a bit further. All right. So well done, Florence. Anyone else? Any comments from anyone else? Any comments or questions? Come on, guys. This is an interactive session, so you're more than welcome to ask questions or comments. Right? Okay, time is up.
Hello?
Yes. Who am I
I
speaking
think
to?
I'm unable to Atem.
Yes, Atem.
I think I'm unable to get the number of rows and the number of columns.
How is that possible? Sorry?
It looks like it is a string data.
It's not let me show you. So after running this piece of code, you should actually go here where it says environment, and then it will tell you 10,000 observations and 23 variables. Can you see that? Hello?
Hello?
Yes, Atem?
Yeah, my data come, but it doesn't come the way yours is.
Did you read it using read.csv?
Yes. Let me retry again.
Yeah,
That's what I need.
Yeah, retry again. Okay. Cool. So I want you guys to look at the data for sex, okay? So the variable sex is a character, right? And has got these values, male, female, okay? And these are not good for us to do any type of machine learning analysis if we want to include those as predictor variables or inputs into our machine learning algorithm, okay? We need a way in which we can encode them into numeric values. Now, we had a suggestion from, is it Florence? Was it Florence? It's Florence, right? It was Florence?
Yes, please.
Who said that we must encode these values instead of it being male and female, we must make it 1 and 2 so that we can calculate the numeric distances. Okay. So however, if we've got 1 and 2 here, it's still fine at a 1 and 2 level. However, if we had, let's say, a variable called color, and it had different types of colors. So let me give you an example here. So here we've got a variable called color. And we've encoded this variable, and 1 is red, blue is 2, green is 3, blue is 4. Because now these numbers are assigned to each and every color, there's gonna be some kind of bias towards the blue color because blue has got a very higher number as compared to red if I had to calculate numeric distances. Okay, so the distance from blue to green will be a lower number. So that will be like, if I'm calculating the Euclidean distance, could be 1. But the difference from blue to red, it's going to be a very, very big number. Okay, so now this basically introduces a lot of bias if we basically go ahead and just do an encoding in this fashion. What we need to think about, or when we do encoding, is not to just do an encoding in this fashion, but to use what we call hot one encoding. Now, the hot one encoding will ensure consistency between all the variables in terms of distances. So for instance, here, we've got color red, which is 1 here. This one here is 0, 0, because for the first observation, we only have color red. So color blue is going to be 0 and color green is going to be 0. For the second observation, we've got color red here as 0. It's not in the second observation, but color blue is in the second observation, while color green is not in the second observation, and so forth. Okay, so the way to transform this data is what we call hot one encoding, to ensure that we don't have inconsistencies between the distances, especially for categorical variables. Okay, now how do we do this in R? That is the next demonstration that I'm going to be showing you, how to do hot one encoding in R. Okay, so to do hot one encoding in R, there's a number of lines that we're going to be using. So first we create a data frame called DMY, which stands for dummy. And then we're going to use this function called dummy vars. And dummy vars basically comes from this library called caret, which allows us to create or to do hot one encoding. So we first run this piece of code, and then we create another data frame called transformed, which is basically the transformed data. So what this piece of line does, it basically creates those dummy variables for each of the categorical variables. So in this case, the variable sex, it's going to create a categorical variable. It's going to create the male sex and the female sex variable, and assign it a value of 1 when it's a male, and 0 when there's no female. And then for the other observation, assign a value of 1 for female if it's there, and 0 for male, and so forth. So it's going to do this for all the categorical variables. Okay. So I'm just going to run this piece of code here. Just want to show you how the data set is going to look like now. So that's the data frame there. I'm running this now. And then I'm creating this transformed data frame. And you can clearly see that the number of observations is still the same. However, we've extended in terms of the number of variables. Okay. Now, if you look at the variables, now we've got the sex female and the sex male. Okay. So in the first observation, you can clearly see that this guy was a male. So that's why sex male has got a value of 1. And this one has got a value of 0. Second observation, that was a female. That's why it's 1. And this one is a 0. And you can see that the third observation, the person was a female and it was not male. So that's why it's 0. So let's see if it aligns to our original data. So if I look at the original data, it was male, female, female, male. And so it's male, female, female, male. And if we look at this transformed data, it is male, which is 1 there, female, female, because of the 1s there, and male. Okay, can you see that? So basically we have hot one encoded our data. And now this data is suitable for analysis for any type of machine learning. Okay, so there's other types of encodings. Basically, it's to make sure that there are no biases, Florence, in terms of calculating the distances. So for instance, if I had to calculate the distance from, I mean, here I'm just only using two numbers, 1 and 0, okay? But let's say if I encoded my data to have maybe values of, let's say 1, 2, 3, 4, 5, 6, 7. If I had to calculate the distance between the value which was encoded with 7 versus another value which was encoded with 1, now that's going to create a huge distance between the two, and then it's going to bias my data. Okay, so that's why hot one encoding is the preferred method. Right. So here I have hot one encoded all my data, and now it's suitable for further analysis. So in this piece of code here, I'm not going to choose all the variables, okay? There is ways in which you can choose the suitable variables, but in this case, I'm choosing the variables that I want to analyze. So here I'm saying select the transformed data frame, and I'm choosing my columns, okay? Yes, it is okay to use other encoding, but the general rule of thumb is that hot one encoding works better, Florence, depending on the number of values you want to encode. So for instance, when I said, I mean, for male and female, it's only 2 possible values, which is 1 and 2. So that one is not a big problem. You're not going to run into much issues. But now if you've got a value where you've got more than 2 levels of encoding, now that's going to sort of like bias your predictions at the end of the day. So you need to think very carefully around that. So to be safe, I would say just use hot one encoding, or use a similar method which is not biased when it comes to calculating differences between the distances. Okay. So here we want to do the select. So here we're saying select column 2, column 3, which speaks to sex female and sex male. We don't want to select column the first column because it's the ID column. It is very unique. So each and every observation will have a unique column. So this one is not a useful input. Remember, I said that you need to select useful inputs for any type of machine learning algorithm. The ID here is not useful at all. So I'm selecting column 2, column 3, column 4 and 5. So the 4 is the age, 5, 6, 7, here are the income bands. Maybe if I were a bit smarter, I would have actually combined these to calculate the average income, okay, instead of selecting them, what you call this, separately. So it would have been better to collapse this into one by calculating the average income for term 1, term 2, as well as term 3. Here, these are the employment status that have been transformed. So I've selected all those columns as well. And yeah, so I've selected all these columns that I need to do my analysis. So the selection of column is really, really up to having domain-specific knowledge, okay? I'm not a mental health expert, so I took columns that make sense for me from a data science perspective, but otherwise, maybe our mental health colleague specialists might think otherwise. But, you know, this is the first attempt in terms of us trying to build a cluster model. So it doesn't really matter much which columns I've chosen, as long as I've chosen columns that make sense. Okay, so these are all the columns that I've chosen. And then I normalize my data. I put them under the same scale. Okay, so this is very important so that we don't get big differences when it comes to the Euclidean distance that we're going to be computing between the different points, okay? So that's why it's very good for us to scale our data, okay? So without wasting any time, I'm just gonna run this. Okay, so then I'm going to have this my data 2, sorry, my data, there's my data. And it's got all the columns that I've selected. And my data 2 is the data frame that has been scaled. So make sure that you scale your data, otherwise you'll get unexpected results. Okay, cool. Alrighty, so I think now we are going to do the data preparation part. Says here, write the following code to prepare the data for cluster analysis. And I want you guys to answer those questions. You've got 10 minutes. Jewel, can you please respond to Gori's question around where the recordings are normally
Yes.
shipped? Nifata, did you install the Carrot library? Run it. I think it's the install Carrot, and you also have to run the library method for that. Okay, so since you guys have got your, do you have R tools? Can you please send me a screenshot on the chat, Nifata?
Sorry, you want a screenshot of which one? Of the
Where you
error
saying,
message?
are you getting errors? You said you're getting errors.
Yes, I was getting errors. I followed till we loaded the data, but when I put this particular activity for the first one, it gave me an error.
Did you run the
package Carrot successfully unpacked and M5 sums checked?
And what about the
Download
library
package
method?
So that was the message I was getting when I tried to install Carrot. It's saying it has successfully unpacked.
Okay, please share your screen. Let's see what you're looking at.
Okay. Please, can you see my screen?
Yeah, let's see. Yeah, but you know, you need to put library. So just say library Carrot because you didn't load the libraries. That's why.
Oh, okay.
Yeah, you didn't load the libraries. So there's a point where you needed to load the libraries. Let me put it in the chat. So because installing and loading libraries, those are two different things.
Oh, okay. So I needed to do the.
Yeah.
Okay.
So just
understood.
after installing, you need to load the libraries as part of your environment. So I've
Okay.
put in the code. So copy and paste it, then that should work now.
Okay. All right. Thank you so much.
Cool. Okay, where's my clock now? It has disappeared. Okay, you guys have 5 minutes. We're all winning now. Anyone facing issues?
Excuse me, sir, I'm getting an error indicated in the chat. I don't know what's the problem.
Sorry?
There is an error I have shared in the group that I'm getting.
Okay, let's share your screen. Let's see. Let me stop sharing. Let's see your screen. Okay, let's see. T. Yeah, Unexpected error symbol. My data not found. Let's see. Select TRS. Okay, so run that line on DMY, the first one. I just want to see. Run line number 25.
25. I have
Yeah,
run it.
just run line number 25. I want to see.
I've run it.
Okay, so go to your, go to your environment. I want to see what's under DMY. Okay, just go under DMY. Just make it bigger. No, you should expand it, expand it. Like you must click on the arrow, on the blue arrow.
Where?
Not that one, the DMY.
Now how do I return?
So you you need to scroll down. It's a lot.
Oh,
Yes. So close it, DMY.
one.
Yeah. Yeah, I'm okay. That's fine. So run line number, go back to your code. Go back to your code. Run that line number 26.
I've run it.
Yeah, but the thing is, yeah, run number 26. I just want to see. Okay, so that's fine. So open the 26, yes. So do the same way. I want to check what's in T. Go scroll down. It should be in alphabetical order. Yeah, you've got a lot of things there. TRSF. You need to close some of those things. Yeah.
Let me first clear everything.
Yeah, if you clear everything, that means you have to run everything from scratch. Yeah. Run that. Run. Run. Yes. Why isn't
I
that
can't
one
see
run?
the
Unexpected symbol.
I don't know what's the problem with this.
Did you include the stats library? Just include the stats library. I'm thinking that you've got a library which is not sub stats. But I don't think that should cause a problem, but you never know.
This one, the second one.
Yeah, that's the one. Run it. Caret is there. You've installed Caret, right?
Sorry.
Okay, run it.
The same problem.
Maybe it's your, I don't know, that read CSV thing. Why don't you just say read.csv instead of saying read_CSV?
That one, I did create a directory. I don't know how to do it. So that's why I use this.
No, just say read.csv. It should give you the same thing.
Looks like she's missing the closing brackets after DF.
Oh yeah, the closing bracket. Yes, the last one. Ah, yeah. Just after DF. Yes. Nice, nice catch.
Oh
yeah. Yeah.
Thank you
Thanks.
so much.
Sure. Okay, screen 2. Righty. So guys, we should be done. So maybe let me give you guys another minute and then we close this up. Then we continue.
Linda, I'm still getting errors even after running the libraries.
You're still getting like errors?
Yes, it's saying error in data And then there's this bracket saying vars drop equals false. Object of type closure is not subsettable.
Let's see your share your screen again. I just want to check.
Okay. Can you see my screen?
Okay, so you ran your Did you run carrot? So you need to run carrot first.
This one?
Yes, so you need to highlight. So highlight everything from 10 up until 15. Sorry. Just hold on, there's something.
I ran it.
Okay, then click. Sorry, there's a timer that is not trying. Just give me a sec. Where is it? Sorry. Okay, there we go. Right. So yeah, so let's do that again. Sorry. So you must click on run.
I have clicked on it already.
Okay, so let's just run line 22.
22.
Yeah.
Oh, sorry.
Line 22.
Just 22?
Yes, just 22. I just want to see something.
I've run it.
Sorry?
I've run 22.
Okay, so that's not a problem. Sorry, I think your screen is out of. Oh, there we go. Is it me? So I think the problem there is you are. What is this? Sorry, can you please? What's happening here? So you see where you say DMY, where you say data equals to DF. You need to change that DF to data because you specified your data frame as data instead of DF. So it's either you change that to
Okay,
data.
this one should be data.
You can make it data, you can make it DF, but you'll need to change it somewhere. So it must be consistent. Sorry, you're moving a screen and I can't see.
The way it is data equals to data, is it okay? Or should I put DF in 22?
I can't see your screen anymore because you've moved it. I don't know if it's me. Oh, there we go. Yeah, so it's either you do that will work, or on 22
let me stop sharing and share again if you can't see me.
No, it's okay, it's okay. I've sorted it out. So on 22, you change data, you make it DF.
Okay.
And then where it says data equals to data, you change that to DF. Yeah, that should be fine now. So run both of those lines.
I should run both of them together?
Yeah, run both of them together. Yeah, should be fine.
Okay.
Yeah, there we go. Okay.
Thank you so much.
Sure. Alrighty. Okay, so you guys are you're a bit behind Nifata, so you still need to do this part here where you basically extract the data, you select the columns, and then you scale your data. Right. So we are supposed to take a break now. So I'm just going to leave this up running for the next, how long should we break for? 5 minutes? Is 5 minutes enough? Is 5 minutes enough? Colleagues?
Yes, sure.
Okay. So for those who have not yet completed.
I think we should make it 10 so that I can cover up.
Okay. All right. But the thing is, we need to watch the time, but it's fine. Like I said, we do have provision for continuing this course tomorrow, so it's fine. but let's make it 7 minutes, okay? So that we get it right in the middle. Okay, I'll make it 7 minutes. Let's break for 7 minutes, colleagues, and then we back. Okay. So please, guys, make sure that you've got this piece of code working, which is demo number 5, and then we continue. Hi guys, I'm back. Are you guys back? Hello, are you guys back?
Hello.
Yes. Okay. I think let's carry on. Okay, so we're now going to move on to selecting a number of clusters. Okay. Okay. Okay, so we're now going to be looking at creating clusters. Okay. So the first thing that we need to do is select the number of clusters. Like I said, this could go two ways. You can first guess the number of clusters based on intuition as well as domain expertise, or you could run a piece of code to basically calculate the number of clusters for you. So there are two methods that we're going to be looking at in this course. There's another method called the gap statistic, but it's just going to take forever to run. So we're just first going to be writing this following code to basically calculate the number of clusters. It's using the within sum of squares method. And then the other one is using the silhouette method. And then question 3 there is that how many optimal clusters are predicted by the silhouette method? Okay, so let's do that. Well, firstly, let me show you the demonstration. So these are basically the methods that I was just talking about, the within sum of squares method, the silhouette method, and then there's the gap statistic. But we're not going to be doing this one in this course. Last time it took me almost 30 minutes just to get something out of this. So please do not try to run this one. It's just going to take you a lot of time. You can write it out and place it somewhere there in your code so that you know that it exists. It's actually a much more accurate way of determining the number of clusters. But like I said, it takes a lot of time. So we don't want to run that. So this one here is called the elbow method. So I'm just going to run this. And I go under plots, just running this piece of code. Takes a bit of time, but it should give me a plot here. Ooh, it's taking time. So with the elbow method, just want to show you something quickly. So so you're gonna get a graph like this, okay? You're gonna get an elbow curve, okay? So where you basically see this sort of like a point or the elbow point, that is basically the optimal number of clusters that you should choose, okay? However, we know that real data looks like this, okay? So sometimes there's no clear elbow inflection point to identify the correct K. In this case, I could tell you that, no, the correct K here is three clusters. That's what you need to choose. But in most instances, you'll find that your data is nicely smooth like this. So it's not very clear where the elbow point should be. Okay. I hope this thing is finished running or it's still running. Okay. So maybe while it's still doing that, oh, there we go. Okay, so it basically shows me my elbow plot or within the sum of squares. And you can clearly see that there's no clear point of inflection. I mean, I'm looking at 2 there. 2 could be a potential candidate, even 3 as well. Okay, so I'm stuck between 2 and 3. I'm not really clear in terms of the number of optimal clusters to choose. Okay. So one other method to help you choose the number of clusters would be the silhouette method. Okay, I'm also going to run this. It will take a bit of time. Hopefully it doesn't take too much time like the previous one. But this one is to just also give you some kind of confidence that there is a number of clusters. So here you see where the average silhouette width is at the highest. So in this case, it's at the highest at 2. So 2 will be the number of optimal clusters that you can choose. Okay. We can also run the gap stat just to verify our results. But like I said, last time it took me 30 minutes. It can take an hour. It's just too much. So let's not even go down this route. So in this case, my number of clusters is going to be 2. So the silhouette method is confirming what I have suspected with my elbow method, that it could either be 2 or 3 based on the inflection point, but I was not sure. But now looking at the silhouette method, it clearly shows that this is actually the optimal number of clusters that I need to be choosing for this data. Okay. Now going back to the activity.
Sorry, may I ask you a question?
Yes.
Yeah, for example, in the DF data set, the variable numbers were 23. Then when we change to the my data, it's reduced to 19. I don't know, maybe how that was happened.
You're saying what? You're saying
the number of variables in my data set.
Yes, there were.
It's 19 and the initiality was 23. I don't know, maybe how we reduced that.
Oh, okay, that's simple. It's because of this. We selected the columns that we are interested in. So this is where we basically reduce the number of
I see. Okay, thank you. Okay.
Hi, Florence. I've interpreted the graph already. Or do you have a specific question?
Yeah, I'm good. I'm getting errors again.
Okay, we'll look at your errors. Let's first finish this, And then we are going to be okay, please guys, let me know once you are done, please.
Sorry, I missed the interpretation of the graph.
All right, yeah, we'll go through it again. Okay, Florence, can you please share your screen? Let's see. Let's see what your issue is.
Can you see my screen?
Just give me a sec. Yeah, so what's the error?
So when I was running this code, I ran it and it gave me error in do one, whatever. Those ones written in pink.
Let me just give me a sec.
And something introduced by cohesion.
So it means that one of the variables that you've chosen has got a missing value. So let me just check the numbers that you've got. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's fine. Did you scale your data? No. So where it says, okay, so where it says data frame. So yeah. So basically you're reading in the original data frame. That's why. And it's got some missing values. So where it says, so go back to line 32.
Line
32. Yes.
32. Okay.
Where it says DF, you need to change that to my data.
Here.
Yes, my data. So that was a result of missing data. It's one of the variables, and I think it is the, which variable was that again? I forgot the name of that variable. We just got the missing data.
Okay.
I think it was.
So here too, I need to change it to my data, right?
Yeah, I need to change it to my data. Nice, yeah. So that should work now.
Okay. I think it worked.
Yeah, it's gonna take a bit of time.
Thank you so much.
So, can you please stop sharing? So that I can
Yeah,
share.
I've stopped already.
All right. Sure, cool. Now going back. So remember, what are we trying to do here? All right. We are trying to basically calculate the number of optimal clusters that we need to choose. Nefata and Florence, are you guys listening?
Yes.
Okay. Remember I said that there's two ways to calculate the number of clusters. The first one is to, oh no, power's out. Just give me a sec. Okay. I'm going to share my screen again. Whew. So the first way to choose the number of clusters is for you to think about it from a domain expertise, okay? You could, based on your experience, as well as an understanding of mental health and whatever, to choose the number of clusters. So that's one way. Another way is to let certain algorithms do that for you, okay? So we've got the within sum of squares, which can help you to calculate the number of clusters. And this within sum of squares basically produces this graph here, okay? Which is basically the total within sum of squares. And it shows you the number of clusters in the x-axis. Now, the way to choose a cluster based on this within sum of squares is to look for an inflection point or the elbow, okay? Let me just annotate it with red. Yellow is too light. Is to look for an inflection point in this graph. So here I've got an inflection point. So where I've got like an elbow type of situation, okay? And 3 here also looks like an inflection point. So here I've got 2 candidates for the number of clusters. It's either 2 or 3. But looking at this graph, I can clearly see that 2 is much more bent as compared to number 3, okay? So both of these give you obtuse angles, but this one is much more bent as compared to this one here, okay? So if I had to choose the number of clusters, I'll be basing it based on this inflection point number 2. Are we together?
Why 2?
No, because that's basically what I'm saying to you, that this graph here tells you where the number of clusters, how many number of clusters you're supposed to choose. Like, let me give an example again. I need to Google this. Where's my, so check here. Can you see can you see the screen here? Hello?
Yes, I can see.
So I'm going to repeat it again. When you do cluster analysis, you need to determine the number of clusters or groupings that you want to analyze, right? But the scientific way of doing that is through these 3 methods, okay? The within sum of squares, the silhouette method, as well as the gap statistics. All 3 of these are going to sort of like calculate to you, based on your data, what is the optimal number of clusters. So that's basically what we're trying to do. We're trying to calculate how many clusters must we input into our k-means algorithm. Do we understand that first?
Yes.
Okay. So that's what we're trying to do. Now, the first method produces a graph like this. Okay. And the graph like this basically says that at the inflection point where this thing turns around like this is your elbow point. That is the optimal number of clusters that you should choose based on your data.
Okay.
Are we good?
Yes.
Okay. But now, what we know for a fact is that this is an ideal situation. In reality, we sometimes get data like this, where there's no clear elbow point. You can see that the inflection point is not as clear as this one here. Do you see that?
Yes.
Now look at our data. Look at our does this look like the first or the second graph? If you look at this graph, so this is the first graph, this is the second graph. Looking at our graph, does this look like the first graph or the second graph?
It looks more like the second graph.
Yes, it looks more like the second graph. So there's no clear inflection point. So it is very difficult to determine the total, the optimal number of clusters, because It could either be 2 or it could either be 3 because there's no clear inflection point. Okay, I'm stopping right here. Anyone who's still confused, raise up your hand. Okay, so it looks like nobody's confused now. Sorry, guys, I'm having issues with electricity. It looks like my lights went out again, but that's not a big problem. Let me just give it a sec. Maybe it's coming back now. Maybe not. Okay, so this is what I'm gonna do now. I'm gonna stop my share. Okay, and then I'm gonna reshare my screen. Share screen. Okay, cool. Can you guys see my screen?
Yes.
Okay, cool. All right. So within the sum of squares, there's no clear inflection point. We all agree. So it's very difficult to determine the optimal number of clusters based on this graph alone. Okay. Now, if we do the same thing, we are now using a different method called the silhouette method for basically trying to compute the optimal number of clusters. So we're basically trying to check, is there any other method that can give us the optimal number of clusters? So now this time we look at the silhouette method. So we ran the silhouette method and it gave us this graph. Okay. Now this graph is very clear. It tells us that at 2 clusters, that's the optimal number of clusters that you should choose for your k-means algorithm. Okay. It's very clear. Now this one is very clear because it even outlines it for you. So to interpret this graph, the only thing that you are interested in this graph is where this line points to the highest number, to where this line is, what you call this, intersects, okay, in the graph. So this is the most important thing that you need to get out of this. So it's basically saying that the optimal number of clusters that you should actually choose for your algorithm is 2. Okay? Yes. So that's basically all it's saying. So it means now, from a scientific perspective, we are going to be using 2 clusters. If you want to do another verification with a method which I believe personally is more accurate, it's the GAPSTAT. But like I said, this method will take a long time to run, okay, before it will give you the optimal number of clusters. So I'd rather not do that now. But for now, I'm happy with just sticking with 2 clusters as given by the silhouette method. All right. So that's it. So now you've got this. So it tells you that
So I'm wondering, like, the number of clusters, can't we be like, okay, maybe we have not reached that step, like maybe seeing that the model is performing like this when these clusters are selected, something like that.
Yeah, you can change the number of clusters as much as you want.
Okay, thank you.
But yeah, but it really depends on you having that intimate understanding of your field. All right. Which clusters make sense, which don't make sense, and so forth. Okay. So now we're going to perform k-means clustering. So we're now going to be performing our k-means clustering. Here we're going to specify our data set, which is my data 2 here, that we're going to go through k-means clustering. We are going to specify that the number of centers should be 2 because we want to do it at 2 and we start at 1. Okay. So that is our start value for us doing our clustering. Okay. And thereafter, we're going to plot the results of our k-means model. Okay. So I think that is the activity that you guys have to do. Okay. So you're gonna write the following code to perform k-means clustering. You set the seed to 1 to make this example reproducible. You specify your k-means clustering by saying km. K-means is my data. You specify the number of centers, which is 2, and you start at 1. So yes, you can ask a question.
I tried to run the for using the gstart method, and it showed me there are about 23 warnings, and I don't know why that happened.
Which method?
The GAP
Yeah, I
start.
said you must not use that method. It's gonna take you a long time, and most probably the issues are around conversions. So
it gave me graphs, but it showed me warnings.
yes, the warnings most probably has to do with conversion. So you'll need to type warnings. I think you have to type warnings there with the open bracket, close bracket, and then it will show you what the warnings are about. Yeah. Okay. Cool. All right. So now we move on to so we have done our clusters. So let me just run this. Let's see. Make sure that I'm not running the gap stat one. Where is it? Okay, there we go. So I'm running my clusters. And there we go. So I'm basically getting 2 clusters here from my data. So you can clearly see my clusters here. And you can also see some concentrations of data here, even though I've got 2 clusters. And you might say that, okay, I might be actually having 4 clusters instead of 2. What if I increase this thing to 4? Okay. So you're allowed to play around with this thing. So I'm running there. And you can clearly see that it's not separating these correctly. I run it again just to see, but it's not gonna be perfect. Okay, so I'm gonna go back to my two clusters. So my algorithm was on point to say that there are only two types of clusters here, and you've got cluster 1 and cluster 2. Now, to interpret your clusters, there's a couple of ways to do it, okay? You can basically run this aggregate function that I'm going to show you right now and look at the different statistics based on each cluster. So here we're going to be looking at the mean of cluster 1 and cluster 2, as well as the variables of each mean. And then here we are going to be looking at the median, okay, of the different cluster variables within the, within each of the cluster. And lastly, another way to interpret your results is to basically export the cluster values back into the original data. So in your original data, so for each observation, you're going to say, this observation belongs to cluster 1, observation 2 belongs to cluster 2, and so forth. And then you can have a comprehensive analysis in terms of how the data is different between the two clusters. Okay, so those are ways in which you can view your clusters. So let me just run this aggregate function here. So the aggregate function basically gives me this output. Okay, so it basically tells me that what is this? So these are my values that I'm finding here. It basically says that the, what am I running? Is it the mean? Just want to make sure it's the mean, okay? So I'm looking at the mean. So it basically means that in cluster 1, there's almost a identical number of males versus females, okay? Almost 50-50 spread. And the age there is about 44. So cluster 1 has got older adults as compared to cluster 2. The income there in cluster 1, if I'm looking at income 1, income T1, T2, and T3, these guys look like they're earning higher as compared to cluster 2. It looks like the employment status of people in cluster 1 is at 99%, and this one is at lower, which is about 6% employment status. And this makes sense because if you look at the unemployment for cluster 1, it's very low as compared to cluster 2. So that basically tells you that the people in cluster 2, majority of them are unemployed, and as compared to the people in cluster 1. Okay, and then you can go around looking at other variables. So you can clearly see that if I'm looking at stress T1, not stressed, so the guys in cluster 1 are not stressed, are not stressed as compared to the ones in cluster 2, which is about 55% not stressed. Okay, so you've got a higher majority of not stressed individuals in cluster 1 as compared to cluster 2. Okay, so that's basically how you can go about interpreting the results from a mean perspective. If you want to look at medians, you can run this also and look at the median values as well. Okay, so this should more or less give you like some values, but in terms of medians, because these are actual numbers, for these other ones, it won't give you, remember, they are only coded as 1 and 0s, so you won't get much as compared to a mean. Okay. The last thing that you can do is, like I said, you basically write back the value of the clusters back into the final data set. So what are we doing here is that we are saying that we've calculated the clusters. We know that there's cluster 1 and cluster 2. Okay. We know their means because we have sort of like understood them from that level, from a statistical level. And now we want to write back the results back to the final data. So if I now run this, what's now going to happen is that it's going to create for me a data frame called final. Where's final? Final data. There's the final data. And it's got this value of cluster. So it basically means that for every individual or for every observation, it's going to basically assign that observation to a cluster. Okay. And if I want to, I can actually output that results into a CSV file. So here I'm creating a CSV file called cluster_analysis.csv. So if I'm running that, I can go back to my original data. So there's the data set that I've just created, cluster_analysis.csv. I open this up. So I'm writing back the results back to my original data. So there's my cluster value. So this one says this particular observation, who's a male at this age, they belong to cluster 1. This one is female, they belong to cluster 2, and so forth. Okay. So with this in mind, now what you can do is that you can do further analysis to basically check what is the differences between the clusters now, because now you've got this variable now written back to the original data set. You can do further analysis if you just don't want to, do your basic analysis like this here in R. Okay. Any questions? Okay, so I'm just gonna give you guys some time to run this code to find the mean and median of each variable in a cluster. And then I would like you guys to tell me what you can say about cluster 1 versus cluster 2. Okay, 5 minutes or 10 minutes.
Hello.
Yes.
Maybe I need an assistant. The others are working on maybe taking you back a bit.
Mm-hmm.
I'm getting some error in the code.
The code.
Yeah.
Okay, share your screen.
Okay.
Go up, 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 up. Did you load all the libraries?
Yes.
So the minute it says could not find function, it means the libraries were not loaded. So it means that they were not even installed. The packages were not installed. So let's do this. Just hold on. Just hold on. I'm going to give you some stuff on the chat. So just copy that and paste it.
Okay.
Okay, there we go. So you need to install those packages way before the libraries. So copy those and install them. Yeah, so wait. Close bracket. So when you run stuff on R, you just don't want to run everything. You need to first highlight what you want to run. So it's better if you highlight first and yeah. So highlight all those import. So behind caret, you need to put a closing bracket there. So highlight that, highlight the installation scripts. No, highlight all of them at the same time. Don't do them.
All of them, okay.
Yeah. Yeah, just say no. No.
I say no.
Yeah. No. 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 Yeah. So it looks like there are some which were not installed. Okay, so that's why it's installing them.
That's fine then.
Let's say no. Yeah, so you should be fine now.
Why is the last one showing red? Still.
Go up. So if you can't find the function, it means that the library was not loaded for that function. So go up.
Oh yeah, I should have the library.
Yeah, I should have the library. So I'm gonna give you this. Yeah, all those libraries are supposed to be loaded. The Vector extra library is supposed to be there. The cluster library, the caret library. Make sure that this library is also working. Okay. Try that again.
Good. Thank you.
Sure.
Oh, another one.
That's because you're reading a wrong data set. You're supposed to be reading, instead of DF, you're supposed to be reading the my data. So on FVis, so the reason why a cluster will throw an error like this, I want you guys to understand something. It's because of missing data. Missingness is a problem for cluster analysis. It doesn't want missing data. So what
change
you've
DF
done,
to my data.
yeah, to my data. You must make it my data.
DMY.
Yeah, my data. No, not DMY. So look at line 38. Line 38, you assigned a variable called my data. Yeah. So you take that my data, you replace it there. Yeah.
Okay, thank you.
Sure. Okay.
Yeah. Thank you.
Sure. Okay. I'm still waiting for my answers, guys. What can you say about cluster 1 versus cluster 2? 5 more minutes and then we wrap it up. Still waiting for my answers about the difference between cluster 1 and cluster 2.
It show me here on my computer.
Sorry?
It shows me error.
An error?
Yeah.
Can you show your screen? So what are we trying to do? So you're trying to aggregate your data by list, cluster equals to KM, cluster mean. So there's not two open bracket. I think your closing brackets are in the wrong place. So after the second cluster, you see that after the second cluster.
Okay, this one.
No, we are on line 37. We're still on line 37. So there's 2 clusters there on line 37.
Yeah.
So the first cluster, the second cluster, yes. Right after the one, yes, right after that one, you need to put a closing bracket.
Okay.
And then remove the last bracket from mean there. It's not supposed to be there. Yeah. And that should be fine.
Thank you.
All right. Okay, I'm still waiting for my answers, guys. What can you say about cluster 1 versus cluster 2? You've looked at the means, you've looked at the median. We now want to get a profile of the clusters, okay? So you now know that we've got 2 clusters, 2 main clusters. What can we say about them? At a very high level.
So Linda, I don't know if, so what I got for the mean, I am seeing that in cluster 2, we are having a negative values for most of the variables as compared to those in cluster 1. For example, if you look at the sex male, you see that the value for the cluster 2 is negative, while
negative. Not
yes, I'm
supposed to be
seeing negative values.
Let's see. Maybe you did something wrong. Share your screen.
Okay.
Negative values are not bad. It's just that very difficult to interpret.
So that's why I said let me say something. Can you see? That's the result here where my cursor is.
I can't see it. That's the thing. Scroll
Can
down.
you see?
Yes, I can see now.
So if you look at for the mean, or are these not negative values? This one?
No, it looks like they are, but there's something not right there. Let me think. So
Because that was the I got.
let me think what could possibly have happened. Let me just think. So you calculate your means. So you scaled your data. That's correct. Data 2, you did your k-means, clustered with it. And then you aggregate based on your data. So I just want to check something here. So can we change your my data to my data 2 because it's a bit confusing. So on line 26, let's make it 20. Let's make it a very different variable.
Line 26.
Yeah, line 26. Make it my data 2.
I should call it my data 2.
Yeah. And then
That's where we are scaling the data.
Yeah, that's where we're scaling the data. Yeah, that's fine. So now on your k-means clustering algorithm,
do you want me to run that 26 first?
Yeah, run it first, yeah.
Okay.
Then what we're going to do is we are going to look. Those numbers don't make sense actually. They don't make sense at all. Then go to to your k-means clustering. You're gonna make it my data 2 under k-means.
Which one? Which line?
Line 41.
Okay.
Line 41 k-means my data 2.
My data 2.
Yes. So run 41 and 42. Sorry, 42 supposed to be my data 2 as well.
My data 2.
Yes. So run both of them at the same time. I just want to check something.
So I should run from
set seed 1, yes.
40 to 42.
Yeah, just run that. I want to see the cluster that it gives you. So I just want to check your cluster plot. Okay, there we go. That's fine. And then on your my aggregate, just do my aggregate of data 1.
My data
2. No, just do it on my data. Let's see. Oh yeah, just do it on my data. I just want to check something. But it's not gonna make it. Yeah, just run the line. No, just run the first line only.
I'm still seeing negative numbers.
Make it my data 2.
Still negative numbers.
Still negative. So let's see, what is it saying? Your ages are not making sense because you're looking at the mean, right? Hello?
Yes.
So if I'm looking at your cluster 1, it basically says that 72. Just give me a sec. Just want to check something. Yeah, there's something wrong. Those numbers don't make sense if I'm just looking at the clusters, because you should have almost the equal distribution in terms of the males and females.
Yes.
Across the clusters. Something is not right. Are we using this? So scroll up. Let me check what you're doing. So let me check something. Sorry, no, go up. So I think this thing is a problem from the word up. Go up, scroll up. Stop right there. So run df, the first line 22. Run line 22.
Library 2.
Line 22.
Okay.
Just run line 22. Just make sure that you got those 10,000 results.
Yeah, I've run it.
So that's fine. And then we create the dummy variables. That's fine. And we create.
You want me to keep
them
running
using-
it as you're saying?
No,
for
no, no,
me?
wait. Don't run anything. I'm just trying to follow what you've done. Then you predict the DMI new data is equal to data frame. Okay, and then you say TRSF. My data to scale my data. Yeah, so just highlight from 23 up until
Was
26.
this supposed to be my data too instead?
It doesn't matter. So highlight from 23 up until 26.
23 up until 26, yeah.
Yeah, just run that. Okay, scroll down. Down.
Done.
Down. Then run run 40 to 42 again.
Two.
No, 40 to 42. 40, you must include that seed, otherwise it's just gonna
Sorry.
be. Is it the data that I gave you that you're using?
Yeah. Yes.
Okay, that's fine. And then run the line 45.
Only 45?
Yeah, just 45. Still give you the same.
Some negatives, yeah.
Okay, just make it
Maybe
my
someone
data.
else can share his screen. Maybe someone else.
Yeah, just run 46. I just want to check what 46 gives you.
I should do what?
Just run line 46.
Line
46, yes.
and 46 is not giving me negative.
No, 46 obviously it won't give you negatives. I'll have to check out like why is it giving you those weird values. I'll have to check, but I don't think this is the right. Yeah. So you can send me an email afterwards and then I'll check it for you.
Please kindly drop your email address.
Yes, I will drop it. Let me just give it to you now. At mrc.ac.za. Okay. So there's my email address. I'll check it out for you. You just send me a script and I'll have to work through it and just check. But I'll send you guys the examples that I've put in this course so that you guys can be able to work on them later. Okay. Any questions? Okay, so all right, so we are done with activity 7, which was basically interpreting the cluster results. We used the mean as well as the median for that. And we could see that cluster 1 has more employed people as compared to cluster 2. And therefore, we've got less stressed people in cluster 1 as compared to cluster 2 who are more stressed, most probably because of unemployment. And we can see also in cluster 1 that the income is higher because of more people being employed as compared to cluster 2. Okay. Then we went through the demo to exploit the cluster results. This was to basically export the clusters back to the original data. So you are basically saying that you are aggregating you're not aggregating, but you're taking the clusters and then mapping them back to each of the observations coming from the original data set so that you can do further analysis. Okay, so if you want to do much more fancy analysis based on the cluster analysis without having to use R functions, you are more than welcome to write back the cluster values back into the original data. Okay, so we did that by doing the cbind function, and then we wrote back the values of the final data frame back into a CSV file called cluster_analysis.csv. Okay, and then we opened that CSV file and confirmed that the cluster variable was exported to the original data set. Okay. Are there any questions or comments? Okay. So, ladies and gentlemen, this was a very quick introduction to cluster analysis. I hope you enjoyed the course. I know we had to go through some of these things very quickly. However, that's how it was designed, just as an introductory course so that everyone can get familiarized with unsupervised learning. So all in all, unsupervised learning is all about trying to do data exploration or pattern discovery, or what we call data mining. We don't use labeled data. We use unlabeled data to basically feed our data through a machine learning algorithm. We don't know what the predictors are. We don't know what the target variable is. So that's the whole essence of doing unsupervised learning. And here we've went through a practical demonstration of applying a machine learning algorithm called cluster analysis, or the k-means clustering algorithm, to basically mine our data. And what we've seen out of that is that there are two distinct clusters coming from the mental health data that we've just analyzed. Okay. So here are my contacts. If you want to us to chat any further, there's my email address, linda.maoi@mrc.ac.za. That's my X handle, but I'm never on X. So